In this video, you and I are going to address stealing bits, host bits, and allocating them for network use, and moving the mask to represent that we've made a change in the network. Here's the opt-out section for this video. If you are comfortable with the answers to these questions and you know the finger game and how to calculate the number of bits to use for custom subnetting, I'll see you in the next video. For everybody else, you are in for a treat. Let's begin. I'd like you to imagine that you and I have shown up for work one day and our boss meets us with a big smile on their face and says, "Can you help me with a small project I'm working on?" And we say, "Sure, what do you need?" And our boss shows us this topology right here that they have drawn like on a napkin or something during a lunch. And they ask us, "Can you put this together? We have a pilot program we're doing and I want to just test some things. Can you make that all happen?" And we say, "Sure." We've got some extra gear, so we round up some routers and we connect them with switches. We even have a back-to-back serial connection right here between R2 and R4. Maybe we use the 192.168.2.0/24. And for the network between R4, R5, and R6, right here, maybe we use the network 192.168.3.0/24. Now, once we've implemented these IP addresses, we go back to our boss all proud and say, "Hey, we're all done. Take a look." And he looks at it on paper and says, "Oh, I forgot to tell you something." And we say, "Oh, what's that?" And the boss says, "This kind of needs to fit into our existing network. And if you could," says the boss, "I need this entire topology to fit in this space of 192.168.5.0/24. I want to use that network to support this entire topology." Now, at that point, we have a couple of options. One, we could say, this is only one network address. We have three individual separate networks that we need. Or the other option, my friend, is to go ahead and do custom subnetting. The process of subnetting is simply taking an existing network space that we're given and chopping it up into smaller pieces. Sort of like if we had Sunset Street, for example. So if we had Sunset Street, which is a physical road somewhere in some town, and we needed to break that up into smaller sections, maybe we could have like Sunset Boulevard, Sunset Avenue, Sunset Lane, for example, and we can break it up. All we're doing when we're doing custom subnetting is we're taking one network address space, like the 192.168.5 network, and we are going to chop it up into smaller pieces so we can make additional smaller networks. Now, unfortunately, there is a price that's going to be paid if we take a perfectly good network like 192.168.5 and we chop it up. This network, which currently has 24 bits for the network and an 8 bits over here for the host portion, in order to do custom subnetting, what we have to do is we are going to say goodbye to a few good host bits. Those 8 some of the bits over in this host portion from the network that we're dealing with, and we are going to allocate some of those bits over towards network addressing. And effectively what it's going to do is going to make more room for network address space, and we're going to use that additional space, those additional bits, to carve out additional subnets. So let's use a practical example here. Let's say we do have a 192.168.5.0/24 network, and we have to use that major network to go ahead and create additional space. The very first question to ask us in this scenario is, how many new networks, or new subnets, if you will, do we need to create for our topology? In this example, we need 1, 2, and 3. So step number 1, I'd like you to write this down with me, is identify number of new subnets needed. because that is the very first step. Identify the number of new subnets needed. So once you've got that jotted down, I'm next going to share with you how you can calculate how many bits you need to take. I'm talking about stealing bits from the valid host bits which are currently available, and we're going to sacrifice them to network address space. And that's done through something called the finger game. Now, if you're wondering, Keith, what the heck is the finger game? You're not going to have to wonder too much longer because we're going to play it together. I'm going to do this literally with you. So here's what I'd like you to do. I'd like you to look at your fingers and include your thumb in that discussion. So look at your fingers, and I'd like you to imagine that your fingers are bits. So if you hold up all your digits on your right hand or your left hand, you look at them, how many digits are there? How many bits are there? And the answer for most people is going to be 5. Unless you're like my shop teacher in high school, but that's another story. So let's go ahead and use the presumption that most people are going to have 5 digits on their hand. And for this game, each of those digits represents a bit. So here's what I'd like you to do. I'd like you to go ahead and act like Fonzie from Happy Days. If you don't know who that is, I'll go ahead and walk you through this. You're going to make a fist with your right hand, stick it out in front of you, and then stick just your thumb up in the air. So with your thumb in the air, I'd like you to look at the back of your thumb, look at your thumbnail. I'd like you to imagine that somebody took a black permanent marker and they wrote right on your thumbnail the number 2. So look at it, see it. What kind of a font did they use? Is it clean? Is it sloppy written 2? But see that 2 on the back of your thumb, and here's what we're going to do. If you only need 2 new subnetworks, all you need to do is steal or take a single host bit from the current available host bits to accomplish that. So the 2 is on your thumb represents that 1 bit, and that's the formula. Now in our case, we need more than just 2 subnets. So here's what we're going to do. With your thumb still up in the air, we're going to go ahead and bring up another digit, like your now 2, that's how many bits it takes to generate that many subnets. Just for grins, that meets our needs. All we really need to do is take 2 bits, and that'll create 4 subnets, which meets our need of 3. So let's do this. Let's start. There's a 2. And the next thing we're going to do is bring up our pointer finger and verbally double that number to go to 4. And bring up another finger, so we have 3 digits in the air, and double the number to 8. Bring up another digit, double the number to 16. Bring up another digit. Now all 5 digits are up, and double that number to 32. And I want to remind you what the importance of this game is, what the relevance is. If you look at your fingers, you've got 5 digits in the air. That means if you take 5 bits away from the host addresses and you allocate them for network addressing, you can have 32 brand new is a very valuable skill that'll come in very handy for you. So in our case, we only need 3 subnets to support this topology right here. So just as a review, let's do the thumb game once again, and we want to make sure we're going to identify how many bits it takes to create up to 3 subnets. So we play the finger game by making a fist. We put our thumb in the air. There's a 2 on our thumb. 2 is not enough. We bring up another digit. Because that allows us to have up to 4 subnets, which meets our needs. 1 bit wasn't enough, and 2 bits gives us up to 4 subnets, which meets our need. And the 4th step, and this is the most important, is to go ahead and let do is we are going to modify the mask. You see, for this network at the moment, the mask is only claiming the first 3 octets, the first 24 bits of the IP address space. But now, if we're going to use the additional first 2 bits of that last octet, we need to change the mask. And that, my friend, is how we communicate the details of using additional bits for the purpose of networking. We're simply going to move the mask that many bits to the right, and they're still going to be contiguous. So now it's going to be the first 24 bits here, plus the first 2 of this last octet. The new mask is going to be 26. Now, out of our beautiful IP address space, now we only have 6 host bits available left for host addressing, which is restricting us a little bit on that end. But now we have more address space to play with, so we can create up to 4 brand new subnets. So your expert exercise right now is to write out these 4 steps. And that is to identify the number of new subnets that you need to create. Use the finger game with a 2 on your thumb, with your fingers representing bits and doubling the number every time you bring up a new digit. Remember, start with a 2 on your thumb. And then once you calculate how many fingers are in the air that meet your requirements for the new number of subnets, you identify that. In our example, we only needed to take 2 bits. And the 4th step is to modify the mask to let everybody know about it. And that's moving the mask to the right by that quantity of bits. So take a moment, make sure you have those 4 steps written down. And what I would like you to do is go ahead and pause me, turn the paper over, and I'd like you to go ahead and from memory repeat those steps. If you need to peek over at the other side as a refresher, that's perfectly fine at the beginning. But I want to make sure that you, on your own, know this exact process. When you've written these out and are comfortable that you understand the process that you should go through, go ahead and resume me. And I want to share with you one more technique that's really important regarding the moving of that mask, those 2 additional bits. Now, here's one of the challenges that's going to come up when we move that mask from a /24, which it was, over to a /26, is that how do we actually represent that in decimal? Because when we work with IP addresses, we're putting in dotted decimal. So what does a /26 look like in dotted decimal? Well, the first 24 bits are good for the mask are 255, 255, 255. Now that's not new. We've already been through that in this course. However, what is new is oh, I don't want to have to convert from binary into decimal every single time I put some type of a custom or non-default mask on an IP address. And I'm totally with you. And that's why what I would recommend you do is create this mask values table as well. So right when you sit down to start working with IP version 4 subnetting, you should definitely that'd be 2 bits on, it'd be a total of 192. If we had the first 3 bits on, for example, it'd be 128 plus 64 plus 32, which is 224. And plus 16 more would be 240. And plus 8 more would be 248. Plus 4 more would be 252. At some point, if you work with IP version 4 a lot, you're going to have these values up here absolutely memorized. But until then, what you could do is this. Simply write out this table. Write the weights first, and then simply write the mask values, which the mask values are going to be 128 plus 64 plus 32 plus 16, and that's that top row right here. So for example, if we're using 2 additional bits from the host portion like this, that would be the mask value. There's our dividing line, and we're set. If we had a situation where we needed to use 5 bits for custom subnetting because we had a requirement for 32 subnetworks and we needed to take 5 additional bits, it would look like this in binary. We'd take that one, that one, that one, that one, and that one. We would leave these last 3 bits for host addressing. The dividing line would be right here, and our mask value would be 248. And if you needed to, you could manually calculate that. 128 plus 64 plus 32 plus 16 plus 8. But having this table here is very, very handy. So here are the 2 things that I want you to take away from this video. Number 1, I want you to be comfortable with the idea that we are stealing, we are taking away available host bits and sacrificing them for the purpose of creating additional networks. What used to be host bits, what used to be a large group of host bits are being whittled away from the high end and being sacrificed over for network addressing. The other thing I want to make sure you're comfortable with is quantity. How many bits do we need to take in order to create a certain number of subnets? And that's all about using the finger game. And to confirm that you get that game, here's what I'd like you to do right now as an expert exercise. I'd like you to do a scenario where you need to create 42 new subnets. So here's my question. If you needed to create 42 brand new subnets, how many host bits would you have to sacrifice to meet the need of 42? And the cool thing is this. This concept applies to Class A or Class B or Class C addresses, because maybe you have a 10 network that's starting with an 8-bit mask, or a 172.16 that's starting with a 16-bit mask, or a 192, 168. Where the host bits start. And from a network that has a /24-bit mask, we would start stealing the actual host bits from the host bits portion, which in this case is the 4th octet that we would begin stealing from. The actual quantity calculation doesn't change. It's all a matter of how many bits this is going to take to create a certain quantity of subnets. So here's what I want you to do right now. Go ahead and calculate using the finger game. How many host bits are we going to have to sacrifice to network addressing in order to get 42 subnets? Go ahead and pause me right now. Go ahead and do the finger game. If you're in a cubicle and people can see you, it's perfectly okay. Get those fingers flying, starting with that 2 on your thumb. So go ahead and pause me and do that now. All right, so let's see how you did. I'm going to go ahead and I'm going to do my thumb in the air right here, and this is going to be my fist. And on the back of my thumb, I've got the number 2. So that's where we start the finger game, is a number 2 on the back of our thumb. So our goal is to get up to 42. That's how many new subnets we need. So we put our thumb in the air, we say 2, that's not enough. We bring up another finger, and we go to 4. That's not enough. We bring up another finger. We go to 8. That's not enough. We bring up another finger. That's 16. That's not enough. We bring up another finger. That is 32. And that is not enough. So if we sacrificed 5 bits for custom subnetting, we would only get 32 subnets, which isn't enough. So what do we do in this situation? The answer is you keep that one hand with all 5 digits up, and you bring up the other hand and continue to double. So on our other hand, so I'll bring up another finger there, and we go to 64, and we stop, because 64 will meet the requirement of 42 subnets. And here's how the counting goes. We have 1, 2, 3, 4, 5, 6 digits in the air. That means we need to take 6 bits. And bits will it take using the finger game and then changing the mask to reflect that. So if we're taking 6 more bits, let's apply that to changing the mask. In the case of a current mask of 8, the new mask would be 14. We're simply adding 6 bits. In the case of 16, the new mask would be 22, 16 plus 6 more. And in the case of 24, the new mask would be 30. So the new mask for the second octet for this network would be 252. The new mask for the third octet would be 252. And the new mask on this network, the 192.168.5/30, that would be in the fourth octet, the mask would be 252. It's representing on each of those networks that we're stealing the additional 6 bits and allocating them for network address space. And the concept is the same for each and every one of them. In the next video, I'll walk you through how to go ahead and determine the actual values of those additional subnets. All right, here's the action items for us in this video. Number one, if you haven't already done the expert exercises, which absolutely include the finger game, I would strongly recommend you practice that and make sure you can do those calculations. Secondly, before you leave this video, go back and revisit the opt-out questions near the beginning just to verify that you can now answer those questions and that you are comfortable with them. I appreciate the time that you've invested in this course with me. I've had a great time. I hope this has been informative for you, and I'd like to thank you for viewing.